Yeah, thanks a lot, Alessandro, for the introduction, and thanks to the organizers for giving me a chance to talk here. I mean, I think the person to blame is Ribu Kaul, whom I met a month ago at a conference. I started to explain to him this problem and say, oh, you should maybe give a talk there. And that's why I end up giving a talk now on this on this problem of chiral melting. Before I forget, I should say that all the work has been done either with Natalia Shepiga, who is a former student in Lausanne, who is now a professor in Delft, and with Samuel Nikes, who is a PhD student in Lausanne now, starting his third year of PhD. And part of the result that I will talk about were also done in collaboration with Jeanne Colbois, a former student from Lausanne, who is now a postdoc in Toulouse with Nicolas Laflorencie. So what is the scope? I will start by telling you the story of a classical unsolved problem of the 80s, an old problem, the commensurate transition in 2D for period 3 systems that has at that time attracted a lot of attention, but wasn't really properly solved, mostly because of the lack of appropriate numerical methods. And it raised a number of questions that now resonates with conformal field theory, but this work was done before, as I was saying, before CFT in 2D was actually solved. So a number of the questions were actually left, not even formulated in a modern language. And this problem was then forgotten because, well, after a while, if you can't solve it, you forget about it in the mid-90s. And then it reappeared a few years ago in a 1D quantum version in the Rydberg chains. There are some experiments done on Rydberg chains, and the quantum model describing these chains has properties that should fall in the same universality class, and that should be another way of looking at a incommensurate transition. And then the whole story started again, and some simulations have been done, and we have done with Natalia Shepiga, DMRG, the density matrix renormalization group investigation of this model. And clearly we could do a much better job than anything that could be done in the 80s. And we found evidence of a very strange chiral transition, which is the main topic of this presentation. Then we decided to go back to the old problem in 2D that could not be solved in the 80s with Monte Carlo. And we used a more recent method, one known as quantum transfer matrix renormalization group, a method that has been inspired by DMRG. That turns out to be extremely powerful for this kind of problem. And again, we found evidence of a chiral transition. And then finally, this is maybe what's, I want to keep it for the end, because maybe for some of you, that's going to be what is most interesting. There is something strange about this transition and this story. And in the context of CFT and the C theorem, and this is what I would like to explain to you, a puzzle we have at the moment, or maybe a conjecture or some naive expectation. So, first of all, a slide just for generalities on phase transitions, a very simple way of looking at it. Phase transitions were, the first important concept was scale invariance at the critical point. I think this is from the mid-60s. And one of the conclusions is that the correlation length has to diverge with some exponent, which is called nu, one of the consequences. Shortly after, Polyakov suggested that maybe there is more than just scale invariance, but conformal invariance. And if a transition is conformally invariant, then in particular, the exponent of the correlation length should be the same in all directions. Doesn't mean that the correlation length is the same. Of course, it could be shorter or longer, but it should diverge with the same exponent. And this conformal invariance is in principle is possible in all dimensions, but it became really a very powerful tool when one realized that in 2D, conformal invariance constrains the theory a lot. And there is a series of minimal models with well-defined exponents that are just rational numbers that can be calculated. This appeared in 1984. And from then on, one has thought very differently about 2D phase transitions, classical 2D phase transition, or even in quantum 1D model, because in most cases, the critical points will belong to one of these minimal models, unless they have a central charge one, in which case there is more universality classes somehow. And finally, the last thing that we all know, that physics in certain dimension is equivalent to quantum physics in one less dimension. So in particular, classical physics in 2D should be equivalent to quantum physics in 1D. So if we have quantum phase transitions in 1D, they are expected to belong to two-dimensional universality classes. So that's just the map of what I think at that level we should. The language is probably the same for all of us. So how do I go down? Now let's look at one specific transition. That's a problem of the late 70s or early 80s, when people studied surfaces, where you could have some surface reconstruction or some layer that were absorbed on surfaces, realizing some periodicity. And let's consider with Ostlund and with Hughes and Fisher a case where we have, for instance, 3 types of domains. So imagine that we have some order in the system which is going to be ferromagnetic Q equals 0 in one direction, but we occupy only every third site, and this defines 3 phases in the perpendicular direction depending on where the occupied site is sitting. So this defines 3 types of domains, and since we have 3 types of domains, if there is a phase transition in the system, it's reasonable to expect it to be 3-state pots. But as noticed by Hughes and Fisher, this is not so simple. Why? Because if we look at the domains, to have suppose we have big A domain and we have B and C's, to have a sequence ABC is not the same as to have the sequence ACB. The domain walls are different between these phases. In one case, for instance, we will have one empty site between a pair of occupied sites, whereas in the other type of domain, we will have 2 occupied sites near each other. So this means that there is something fundamentally different in that problem, and this is what they assimilated to a Chiral perturbation, and with this perturbation they came to the conclusion that the transition can be in fact very different. So a very minimal model that would describe this is what they call the Chiral 3-state pots model. It's pots, so it could be also clock, pots and clock for 3 states are the same. So sometimes it's also called the 3-state clock model. This is a model where, to keep things simple, but it doesn't matter very much, there is a simple type of coupling typical of pots in one direction here, where we have a cosine and 2 pi over 3 times the difference of integers. And if the coupling constant is positive, we want all the integers to be equal, but they can be all equal to 0, 1, or 2. Hence, we have three types of possible orders for that one. But in the x direction, one can add a parameter delta that can take non-integer values that will change the physics, and that will shift it, and that will induce a chirality that is a difference between positive and negative difference. That is exactly what chirality is about in that context, so that the difference will be biased in one direction as compared to the other. And then under these conditions, Hughes and Fisher suggested that there is the possibility for that model to have still a direct order-disorder transition from a commensurate phase to an incommensurate phase, but that this transition will not be conformal. They call it a Chiral transition. And at this transition, the main difference with the conformal transition is that the critical exponents of the correlation lengths could be different in 2 directions. This is actually a very general property they predicted, and it has nothing to do with the fact that delta is only in one direction. The model that would have incommensurability in both directions is also expected to have 2 different correlation lengths, but then they could be in the direction x plus y and x minus y. But as soon as there is some shift in one of these couplings, we expect to have 2 different correlation lengths. At least this is the suggestion by Hughes and Fisher. And then there would be an exponent. It's in the classical context, it's called usually an anisotropy exponent, which is the ratio of the 2 correlation length exponents, but for 1D quantum system, it's called dynamical exponent, and I think this terminology has become really dominant. But there is a dynamical exponent which is then different from one, larger than one. And the other possibility, the alternative is to have, instead of having a new type of transition, is to have a two-step transition from an ordered system to a disordered system through a critical phase. And that's a two-step process, so there would be an intermediate phase. In this phase, the wave vector is changing, so it's like if it was floating in terms of answer base. So the name floating phase was coined on this type of phase. And according to Hughes and Fisher, this is also a possibility. It's also realized, but it's realized beyond a certain finite value of delta. That is, we start increasing delta. First of all, they suggested that we should have a chiral transition, non-conformal, and then an intermediate floating phase. So the phase diagram, let's look at the right-hand side. The left-hand side deals with something else. The parameter, which is called theta here, is somehow increasing the chirality. And the transition as a function of temperature is going to be pots at a given point. And according to them, there should be a transition here, which is chiral, with different correlation length exponents. And then there should be a Lifshitz point where an incommensurate critical phase opens. And this transition, and this is easily understood in 1D fermionic language, is first a Pokrowski-Talapov transition. It's very much like, if domain walls are considered as fermions, it's very much like starting to fill up a band of fermions. So this is a non-conformal transition with Z equal to, it's in the free Fermat language, it's a rather trivial transition. And then there would be a Kosterlitz-Thouless transition where the correlations stop being critical and become exponentially reduced here. So that's the phase diagram, a proposal they came up with in the early 80s. And in field theory, in the language of field theory, I'm not an expert, as Anders was saying also this morning. So, but in field theory language, if we define an order parameter which is complex, this means that in the Hamiltonian for the Landau-Ginzburg theory or the action, there will be a term which is only proportional to the first that contains only one derivative of the field. So it's a field of that type. Because the field is odd under parity, I think there has to be a minus sign here because of the difference to get something real. So this is a chiral term. This is a perturbation. And the problem is to know what is the effect of this perturbation on the Potts model somehow. Now, they argued, Hughes and Fisher, that the perturbation is in fact relevant. And I think there is a CFT, there is a very simple way of understanding this from the point of view of CFT. So this is what I'm giving to you now, although these arguments came much later with Cardy in the early 90s. Well, at the Potts point, is we are in the three-state Potts universality class when there is no perturbation. But at that point, we know what the content of the CFT is, and there are operators with dimension H and H bar equals 7/5, 2/5, and 2/5, 7/5. So both these operators have a scaling dimension 9/5, the sum of the two, which is smaller than 2. So we know they are relevant perturbations. So this means that very clearly, and well, there are arguments saying that this chiral perturbation couples to these operators. So if we look at it as the CFT perturbed by some operator, these are the operators to consider. They're relevant. So we cannot stay at the Potts point. That's very clear. So something has to happen, and I think there is no doubt about this. Now, concretely,
sorry, Fredric.
Yeah.
So these are not scalars, right? These are currents.
Yes.
So okay, so that's why you break. That's why you get the dynamical exponent, because you're breaking Euclidean rotation.
Yeah, so you would get a dynamical exponent, but we don't know which one. I think yes, these are. It could be 2 if we were Pokrowski-Talapov, or it could be something else. Yes, I don't know if that's your question.
Thanks.
So where was I? So now, at that stage, the question was, this is a proposal. It's a possibility, but it's not clear that it's going to be realized, that we have this transition. We could simply have an intermediate phase, and in fact, a lot of people believed at that time that this is the case. And how to distinguish? So one thing here is that these operators are relevant, but the scaling dimension is very close to 2. So you can imagine that it's going to be difficult to see this. You can imagine very slow crossovers. And so it might be difficult to determine things very precisely. So what Hughes and Fisher suggested at that time is to look at something very, very simple, not directly related to exponents, which is to measure, first of all, the distance to commensurability, because when we start going away from this phase, we start having domain walls and we have incommensurability in the wave vector. And we can also measure the correlation length in principle. And the product of the two is a very clear indicator of what's going to happen here. Because if we are at the Potts point, it's known that the exponent, the delta Q, is going to go to 0 very fast with an exponent 5/3, whereas the psi is going to diverge with an exponent which is twice as small, 5/6. And so this product is expected to go to 0 very fast for the Potts point. If we have an intermediate phase, this product is going to diverge because delta Q will remain finite when we enter the critical phase where psi has diverged. So the product of the two should diverge even away from the commensurate phase. And if we have another scenario, a chiral phase, this product was predicted by Hughes and Fisher to go to a constant. That is, the exponent of delta Q and the exponent of nu should be the same. This is a quantity which in principle can be measured, the product of the two. So it sounds like it should be easy to solve the problem. It turns out it's not at all. And this came as a surprise to me when I discovered all about this field of the 80s a few years ago, because I thought 2D classical problems, Monte Carlo, where the difficulty? Well, here the difficulty is that we need to have information on delta Q that is extremely precise to see how it scales to 0. And delta Q, the difference in wave vector, suppose that we have a system size which is the inverse of this difference. And here, as we will see, we need information where delta Q is known with a precision of 10 to the minus 4, something like that. So it would mean studying systems of 10,000 times 10,000 or more. That would be extremely difficult. And the first simulation that were done by really totally respectable, excellent physicists, specialists of stat phys, Walter Selke and Julia Yeomans, were kind of inconclusive. That is, the Q vector, it's impossible to know exactly where the transition is. There is some kind of crossover in the Q vector, but it doesn't seem to go really to 0, at least not until 0.1. So they had some evidence that maybe something is happening around 0.4. As we shall see, the more recent results we have suggest that this transition is much smaller value of delta. So, and then this was the first paper. I'm showing it because it was the first. And then in the 80s, different people tried different things, numerical stuff. And I would say roughly half the papers concluded there is a chiral transition, and half the papers concluded there is no chiral transition, but immediately an intermediate phase. This went on in the 80s, and then numerically people were stuck. So the problem was kind of considered, not solved. And there were also some field theory arguments and so there was one important series of paper, one by Haldane, Backenbohr, and the other one by Heinz Schulz, that studied a version, the Sine-Gordon model, and the quantum version. And they found that their conclusion is that they should be an intermediate phase immediately away from the Potts point. I'm not sure they fully characterize the Potts point, but this is a solid model. But as Hughes and Fisher pointed out, this is really a very special case, because in the context of the two-dimensional model they were studying, this would be the case if there is no if these locations are not allowed in the system. If one allows this location, it changes the physics. And Hughes and Fisher came up with this phase diagram where, as a function of the fugacity Z here that would induce these locations, if Z is 0, they accept the result of Haldane, Bagbor, and Schultz that an intermediate phase might open immediately. But if one includes the dislocation, then they suggest that in fact there could be a transition that is first a direct transition before we have an intermediate phase. I will not enter this because I want to show some numerical results. And well, finally, there were two very interesting developments later on. Time flows. So I think at that time, most people that had tried to solve the problem were already lost interest. And Cardy, John, you all know, of course, Cardy in this community. Cardy wrote a paper, like, coming out of the blue on another version of the model, and looked at it with the language in the language of CFT. So he took a model where he put some chiral perturbation, both in X and Y direction, but these chiral perturbations are complex. So this model would correspond to a statistical physics model with complex amplitude. So it cannot be seen as a physical model. But the reason why he did that is that if he takes this perturbation, this self-dual point where delta y is equal to plus or minus I delta x, then he could show that he couples only to one of the operator of the CFT. And this allowed him to make a much simpler analysis than the one if he had the two operators. And with this analysis, he came to the conclusion that one correlation exponent is 1 and the other one is 2/3, very different. So clearly there is something there. For that model, this is kind of a proof. It's rather subtle because it sounds like along the flow, the principal axes for the correlation lengths are rotating. There are a number of things, and it's very difficult to actually change this model numerically. But there was at least for another model, which is not the physical model, and we're not sure whether or not it is related to the physical model, but he came up with these exponents. And then the final piece of information, and this one I like very much because this was ignored. Yes, Subir. Yeah.
Hi. Yeah. Can you hear me? Yeah.
Yes, yeah, I can.
I mean, Cardy's critical point has a lower symmetry than the model that you're studying, right? It doesn't have, I think, time reversal or something like that. And so I'm still puzzled as how it could have any relevance to the Hughes-Fisher critical theory. Yeah.
I think I agree with you. It's the only model where we know that there is such an anisotropic critical point. But he himself said that this could be the Lifshitz point, and this is something I don't really believe because the Lifshitz point, I think, is repulsive in both directions. So one cannot go, I think, from there to the Lifshitz point. I'm sorry?
Yeah, I mean, the same issue applies to the Lifshitz point. At any point in the phase diagram, there's a certain time reversal symmetry that's present in all the theories there, which is not present here. And that's, usually symmetry at the critical point is larger, not smaller than the original UV model. But okay, yeah, it's a puzzle.
I'm quoting this paper not as a theory. It's just one paper that also identified the perturbation in CFT language and did this calculation, but it doesn't solve the problem. I think I agree.
All right, thank you.
And the last paper before the problem was forgotten was an experimental paper by several people, including Bob Birgeneau, who measured this. So that was a system with a reconstruction 3x1 on silicon 113, measured all critical exponents and reached the following critical exponents. That is, he had really very clear evidence of an anisotropy. And these exponents look very much like those found by Cardy for a completely different model. And in fact, in this experimental paper, they acknowledge the fact that they seem to have measured the same exponents, but that they don't understand why it should be the case. That if they had exponent with the nu y, which is, I mean, roughly speaking, something like 2/3, and this, but these two exponents are equal within numerical uncertainty, and this is the criterion for a Chiral transition, because if both exponents are equal, then the product should go to a constant, and this should be a Chiral transition. So there was this paper that kind of demonstrated the possibility of a Chiral transition, but I believe that the value of the exponents was not predicted in any way. And this is basically where the story stopped at that time. And then it was restarted again because of chains of Rydberg atoms. So let me show some experiments where in the chain of Rydberg atoms, it's a 1D quantum system where there is a chain of atoms that can be excited in a Rydberg state and in a very high Rydberg state, making them very big. So if the atoms are in the ground state, they basically do not interact because the electronic wave function is extremely localized around the site. But if they are in the Rydberg state, then they will interact. And so whenever there is one particle in the Rydberg state, at this side, we keep track of this with the number of particles. And if we have two states in a Rydberg state, two atoms, they will interact, and this interaction decays as 1/R6. So it decays quite fast, but still has a power law. And then there is another parameter, which is, so we have a Rabi frequency, that a laser that promotes state from the ground state to the Rydberg state, and vice versa. And there is a detuning that controls the average number of atoms that will be in an excited state. So this is considered a fairly accurate model to describe such systems. It's written here in terms of a density and then an operator sigma x that can change from one state to the other. One can also look at the model as a model of hardcore bosons, where this is just the sum of a creation and annihilation operator. So experimentally, it was possible to measure different phases as a function of the filling. And so the period 2, period 3, and period 4 phases have been measured here. And then when reducing the tuning here, one can get out of this phase. And these quantum phase transitions are incommensurate transitions that are expected to be in the same universality class as the commensurate, incommensurate transitions that were studied in the 80s in the context of disordered, of adsorbed layers. And in this experiment, one can measure different things. It's quite interesting. One can, in principle, have access to what is called the Kibble-Turek exponent mu that describe the way the correlation length grows as a function of the sweeping rate of the if we sweep the system across the transition. So if we were to do it infinitely slowly, the correlation length would diverge at the transition. But if we have a certain rate, the correlation length will saturate, and the value at which it saturates is related to the sweeping rate. And this exponent mu, if we were in a big enough system, in a very large system, is related to the correlation length exponent and to the dynamical exponent. It's the ratio of nu over nu 1 plus z nu. So measuring this Kibble-Turek exponent gives, in principle, access to one piece of information. And if one can have all the pieces of information, one could come up with a complete description of the phase transition. I will not dwell on this. It's well, at the moment, I think it's still difficult to extract very precise information from this. One has to keep in mind one important thing, that these experiments have been done on a chain of 51 atoms, which is quite short. And I think predictions here that would require presumably much larger systems. This is what we found recently in a more realistic approach, but this is not what I want to discuss today. Just to say that there are experiments going on, there will be new experiments. So this problem again became very important. So Rydberg chains, as I said, are described by this kind of model. We can replace the sigma x. It's like creating or annihilating a Hartrott boson with a repulsion 1/R6. And it's possible to take a caricature of this interaction that should keep the system in the same universality by saying that at certain density, it's very unlikely for two atoms to be very close to each other. So we can put all these repulsions to infinity. And then if they are very far, the repulsion is very small and you can forget about it. So one can construct a model that has constraints and that has only one parameter when the particles are distance p-1 for period p phase. This model was introduced for the case p equals 3 by Fenlis and Gupta and Sachdeva in 2004. And so this means that we have here hardcore bosons, but they have an additional constraint that they cannot be nearest neighbors. So this is what they called hard bosons. The bosons cannot sit at the same side, but they cannot even be nearest neighbor. And that's a model that is very convenient because it's numerically a little bit simpler than the full model, and yet it should reveal the same kind of physics. So this model has been studied, first of all, but not directly in that context, I think, by Fenlis and Gupta and Sachdeva, and we revisited it. And the main features of the phase diagram, I think there is no doubt. We all agree. So I showed the phase diagram we derived with Natalia, but at that level, I do not think there is no claim of novelty in this phase diagram. So we have a period 2 phase in this phase diagram. And but the transition is to a phase which is commensurate. It's not an incommensurate transition because there is a disorder line here. And this transition is Ising down to a certain point where it becomes strike-critical, Ising, and turns into a first-order transition. This is the kind of physics that quite typical. For the period 3 phase, it's very different. It's a commensurate, incommensurate transition, and along such a lobe here. And for that transition, for that specific model, one of the main advantages is that there is an exactly solvable line, which is shown here at the dashed line. This is not a phase transition. This is just a line where the solution can be derived exactly. And we know that this line crosses here at the points which is the 3-state bonds. And so generically, we expect only to have one point, which is 3 states. And for that particular model, we know exactly where this point is. And then the question is, if we go back to Hughes and Fisher, this is a quantum 1D model, but the question is, what is the nature of the transition away from this point? This is what one would like to study. So that's I just said. So there were, well, in 2004, I think Paul Fenley and co-authors found evidence. One of the main things of the paper was to report evidence that there is an intermediate phase for large negative U. Sorry, I want to go back here. That is, here there has to be a small intermediate phase. On that scale, you wouldn't see it. It's smaller than the width of the line. And in the absence of any indication, one of the conclusions was that presumably the intermediate phase remains up to the Potts point. But then when experiments were made and on Rydberg atoms and revealed that this doesn't seem to be the case, it seems there is really a direct transition, then this was revisited by Subi and Sachdeva and his collaborators, his students Samajda and other collaborators. And they reported evidence that there is a non-integer dynamical exponent between Potts and V plus infinity. That is, in this phase diagram, above this line, there was indication that something's happening, that the dynamical exponent is something between 1 and 2, so it's not Pokorski-Talapov, but it's no longer 3-state Potts. Well, I could say this motivated us. In fact, we came with Natalia Shipiga to this model through a completely different routes, studying a one-dimensional version, a ladder version of the quantum dimer model. But anyway, we studied this phase diagram with another form of DMRG. And there, what we could do is, because the Hilbert space grows like the Fibonacci chain, so it grows not too fast. And it turned out to be possible to do simulations that were well converged on very large systems, up to 9,000 sites. And so we were able to determine the delta Q with a very large precision, at least the 3rd digit, along the transition. And for the correlation lengths, we could access very large values. So finally, we could have really meaningful evaluation of the ratio delta Q times psi close enough to the transition to hope and say, to be able to say something about it. And this is the main technical slide of this presentation. I'm going to show in a column here 3 quantities for 3 different points. This is just a benchmark. This is POTS, and we show the inverse correlation length, the incommensurability, the distance to the commensurate vector, and the product of this distance to the correlation length. Sorry, this is just the wave vector, and this is the distance delta q times psi. For the POTS point, we know the exponent nu should be 5/5, and our numerical results are in a fairly good agreement with this. Beta bar, the exponent describing the way q goes to 0, is known to be 5/3. Again, we have very good agreement with this. You see the kind of precision we need to see this, but we see the curvature and that it reaches the value with the that's consistent with an exponent which is larger than 1. And finally, of course, since nu is much smaller than beta bar, we find that the product goes to 0. So POTS, very clear, and it seems that our algorithm is able to say something meaningful about this result. Now, if we go, another benchmark is the point q minus 15, which is in the where the Fenlis and Gutta and Sachdeva were able to show that there is an intermediate phase. And again, there, the algorithm has no problem to detect this. On the contrary, it's very clear. We have a transition out of the commensurate phase with an exponent which is much smaller, which is consistent with 1/2, which is the exponent what we would expect for the Prokofsky-Talapov transition. And on the other side of the transition, the inverse correlation length goes to 0 extremely fast. It's and this is really consistent with the Costelli-Thouless transition. Xi is expected to diverge exponentially. So 1 over Xi to go to 0 extremely fast. The Q vector also seems to reach commensurability with an exponent consistent with 1/2, as it should for Prokofsky-Talapov transition. And of course, since Xi diverges much before, we have the product of the two becomes extremely large and is consistent with the divergence. So again, consistent with Hughes-Fisher intermediate phase. And then with the same algorithm, we looked just above the POTS point, close enough. And there, this is where things become very different from both other possibilities. We seem to have a single phase transition. The correlation length seems to 1 over Xi seems to go to 0 at the unique point with exponents that are roughly consistent with each other. So this means that we should have a single continuous phase transition. The main difference is the exponent beta bar that describes the way Q reaches commensurability. It is no longer reaching commensurability with an exponent obviously larger than 1, but with an exponent smaller than 1, with an infinite slope. Although we are really very close to the POTS point. So there is something very dramatic occurring for that exponent. And well, it's difficult to extract the exponent, but it's clear that the curvature is different. And if we take the product, that's Hughes and Fisher criterion, we get data that are consistent with the arrow bars get big, but it's consistent with something that would go to a constant. It doesn't go to 0. It doesn't seem to diverge. So it seems that indeed there is evidence of a chiral phase transition. And this kind of evidence, I think it goes beyond what was done on classical systems by all means in the 80s. That's very clear. So for the quantum model, we have an evidence, and I think we agree. There were other approaches also showing this, that there seems to be a chiral phase transition. And according to some criteria, we would locate the chiral transition around these points, but it's very difficult to locate precisely the point where it would turn into an intermediate phase. But roughly speaking, this is our numerical estimate of the region of chiral transition. We did the same for the period 4 phase. I will not discuss it, but it's very similar, just that it's not a POTS point, it's Ashkin-Teller. And it's important to know which Ashkin-Teller, because depending on the value of the Ashkin-Teller parameter, the perturbation may or may not be relevant, but we found that it is the value where the perturbation is relevant. And then we also found some evidence of a chiral transition around it, but I don't want to make things more complicated than they need to be. Now, Yes, it's very good. So now, what about, let's go back to the problem of the 80s, classical 2D that was not solved in the 80s. Can we do better? This was what I did, was what I showed was DMRG in 1D. But indeed, there is, very much in the same spirit, and actually inspired by DMRG, a very clever Japanese guy named Nishino in 1995 came with an idea to use very similar approaches to study a classical system using the corner transfer matrix. The corner transfer matrix was one concept introduced by Baxter in solving problems rather than having just a linear transfer matrix. He was looking at the transfer matrix around a corner. And then what Nishino proposed is to make some RG very much inspired by DMRG. That is, the idea is to group sites. So the first starting point is to represent the partition function as a tensor network with Boltzmann weight on the links, and then one can cut them and define tensors locally. So one can see statistical physics as a problem of contracting a tensor network. And then this contraction can be made piece by piece by grouping tensors together. This means that we have a tensor whose dimension is the square of this, but then we can make a singular value decomposition to keep and throw away the very small singular values to keep an approximate representation of the system with a bond dimension, which can be kept then constant during the renormalization. So it's approximate because at each step, of course, we throw something away, like in DMRG. But if we do it way and if the bond dimension is big enough, what we throw away is kind of negligible. So this algorithm worked very well, but has not been used really for many 2D classical systems, mostly because most of them are solved by Monte Carlo. But this particular problem was not. So we decided to go back to it and see whether we can get results that are consistent with what we had for the quantum 1D model. And first of all, a benchmark for the Potts model. I mean, maybe, I don't know if some of you have been confronted to it, but the Potts model is the three-state Potts model is a very tricky model. In particular, the exponent alpha, which is known exactly to be 1/3, is very difficult to get out of numerical simulations because there are corrections to scaling that are very big. I mean, this has been really studied in great detail by Alan Sokol using Monte Carlo simulations in the 90s, and it's extremely difficult to get good exponents. And now, if we look with the kind of approach we have here, we do not have statistical errors, and it's possible not just to fit correlations, but to define effective exponents by the derivative of the logarithm of any quantity with the log of the distance to the critical point. And to look at the way the exponents change upon approaching the critical point. This is a little bit like what Anders showed this morning when he was looking at the size, where you have exponents changing with the size. Here they change, but they change here upon approaching TC. You follow the logarithmic derivative. And for the Potts model, this works very well. We have a distance, very clearly the effective exponent is changing, but the limiting value, for instance, of nu is very consistent with 5/6 here upon approaching TC. The exponent beta bar is larger and is consistent again with 5/3 as it should. And even for the exponent alpha, we are still far from 1/3, but the results are not inconsistent if we fit the specific heat. And in fact, if we fit directly the energy, which has a smaller correction to scaling, we get 1 minus alpha, which becomes very close to 2/3. So this method apparently does already a better job than the Monte Carlo for the three-state Potts model. And then I will keep things short because time is going, but then we decided to study the model I showed at the beginning, the Chiral three-state Potts model. And as a function of delta equals 0 is Potts. And if not, we have this asymmetric model. And the first thing, maybe the most remarkable result we found is that the exponent beta bar, which for the Potts model is really consistent with 5/3, that is 1.66 or so, is completely different here as soon as we put a very small Chiral perturbation, delta equals 0.04. Again, that's very similar to what we had in quantum 1D, where immediately we had a delta Q that was behaving differently. And here beta bar is going to a value that is, roughly speaking, consistent with 2/3. And although again, there is no theory for that 2/3, it's just for a comparison. And if we look at other exponents, the exponents nu have a big crossover effects apparently close to the Potts point. We couldn't get really consistent results, but further away, around up to delta equals 0.16, we can get an exponent nu in the y direction, which is consistent on both sides of the transition. This is the way we determine TC. And then if we use this TC, and if we look at the effective exponent for the correlation length nu x, we get results that are again consistent with the kind of values got for beta bar, that is for a Chiral transition. And for larger values of delta, the transition is very different. It's consistent with Podkowski-Talapov. So the kind of phase diagram we came up with for the Chiral three-state Potts model is a phase diagram where there seems to be a change of behavior, but much earlier than predicted by Monte Carlo, not around 0.3, but around 0.17. Beyond that, everything is consistent with KT and PT, Podkowski-Talapov and Kostelis-Thouless. In this region, it seemed that we have a direct transition. The exponent beta bar is not changing very much, and well, it's written here 2/3, but it's really better to say of the order of 2/3, but it doesn't seem to change very much along the transition. And the exponent nu x, at least in this region, close to this point, is consistent with beta bar, while nu y is roughly of order 1. So there are alternative approaches. I mean, Subir is here, he knows better, much better than me what they did. Using a duality, they could map the system on another problem of bosons with hardcore bosons where you create 3 terms at a time. And doing a loop expansion, they also found that there is an exponent z which is larger than 1. And I don't remember the value, but maybe around 1.6 or something. So something like this. So seems to be that there is something. What isn't clear is whether these exponents are the same. I mean, if we look at the transition along this line, there is this Flischitz point. On this side, we flow to 3 fermions, so this is Podkowski-Talapov. On this side, we should flow in this direction. Sorry, when we flow in this direction, but here we flow in this direction. So maybe in a multi-dimensional space, there is some fixed points there. I must say I don't really know. So just to show, that was the Monte Carlo first. Now, last slides, and then I'm done. What can we say? You know, this Chiral transition was, all these ideas were developed in 1982, and the classification of the CFT in 2D was done later on in 84, and then there was Zamolodchikov's C theorem that was done a little bit later. So most of the discussions about the Chiral transition were done before that. So some of the questions, obvious questions, I think were not asked, and this is what I want to share with you now, although I don't have an answer. The Chiral transition is not conformal, but we have at least 2 phases that are conformal. I mean, 2 phases. The conformal field theory is realized at 2 points. The first one is the Potts point. And at the Potts point, we have a central charge 4/5. This is well-known, it's a minimal model. Now, if we have an intermediate phase, it's a C=1, it's a Luttinger liquid. The floating phase is the Luttinger liquid. It has, in the fermionic language, it has an emergent Q1 symmetry. And so this phase is C=1. And so one question, which is not obvious, I think, is it possible that the Potts point actually touches the Luttinger liquid phase? We have a point with central charge 4/5 and a whole phase with C=1. And so that would mean that the Potts point is here, the increment phase is here, but if, as suggested by Haldane, Back-and-Bohr, for instance, the Lifshitz point is actually moved here, we should have, the Potts point should be in contact with this phase. Now, there might be a problem there, although it's not really a problem, but it's maybe an interesting question. we know there is a C theorem. So if we have an RG flow, I mean, the very naive version of the C theorem is that the central charge should decrease when along an RG flow. Now, the Potts point is unstable because there is a chiral perturbation, which is relevant. So if we are very naive, we would expect the central charge, if anything, to decrease if you reach a phase or point that has conformal invariance. But if we had a Potts point close touching the intermediate phase has C equal 1. So it sounds like we're flowing from Potts with a central charge 4/5 to a Lagrange liquid phase with central charge 1, which, according to the C theorem, should not be possible. Now, is this really a contradiction? This is naive. And because obviously one of the hypotheses of the C theorem is not fulfilled. Lorentz variance is not preserved along the flow. And my understanding, and I've discussed with some people that are much more expert than I am of this, is that at least the proofs that have been done of this theorem really relies on Lorentz invariance being conserved during the flow. So it's not obvious that there is a problem, at least it does not contradict the C theorem in that respect, the way it has been proven. Still, it's kind of strange to imagine that we go, since the central charge measures, it's roughly speaking, the kind of degrees of freedom, or along the flow, the reduction of the degrees of freedom. It sounds a little bit counterintuitive that a flow could bring one from C equal 4/5 to C equal 1. And so now, I mean, I'm going to try and look with colleagues at whether we can dig there and see maybe there is something interesting. But at least these questions look from outside now with all the background in CFT. These are kind of obvious questions that were not asked in the 80s because all this was developed before. So this leads me to my conclusions. Modern numerical approaches can do a much better job than what was possible in the 80s. And I think there is strong evidence now that there is indeed something like a chiral transition in classical 2D models. This is definitely consistent revealed by CTM-RG corner transfer matrix renormalization group, both for the chiral three-state Potts model and for the asymmetric Ashkin-Taylor model, the point I did not really discuss. And for 1D system also, for the blockade models, at least of Rydberg chains, I think there is evidence. And let me quote 3 open questions. I'm sure there are much more. First of all, the last one I did discuss, is there a CFT argument that could be refined to say something about the possibility of having Potts point touching the intermediate phase, or is this kind of excluded by these arguments? Another important open question is the nature of the Lifshitz point. If there is this is a multi-critical point and the nature is not clear in the exponents. And another question is whether, if there is a Lifshitz point between the two, whether the exponents keep constant values, which is what our numerical results seem to indicate, at least for the exponent beta bar, but there is no theory for that. So with these remarks, I will stop and thank you for your attention.
Thank you very much, Fredric. The nice talk. Any question?
Yes, I see one from, I don't know.
Yes, Inchen.
Yeah, so one question I'm curious is, what does the entanglement entropy look like for those chiral transitions?
Wow.
I mean, you can, you know what I'm talking about, like for CFT,
yes.
From the entanglement entropy, you can get single charge.
We didn't look at it. I would have to think about it. We really didn't look at this. That's a good question. I would have to investigate. So you mean, for instance, sitting at the critical point and seeing at
Let's say
the way the entanglement entropy scales with the length of the system, or
yeah, or the length of subsystem size, right? The cut of the entanglement entropy. Right.
It's yeah. Well, one has to think carefully about the possibility. I mean, most of the arguments we have relied on approaching the critical point, not on sitting at the critical point. So yeah. The exact critical point is difficult. And I thought, for it would be, I think it would be most relevant to study the entanglement entropy at the critical point. This might be difficult, but it's an interesting suggestion. Yes.
Yeah, I think as long as you're close enough to a critical point, you can say some meaningful signature there.
I will think about it. Thank you. Thank you for the question.
Yeah, and another question is about this state theorem you mentioned, right? So as you said, the state theorem measures the number of degrees of freedom, like Gabley's degree of freedom of the theory, right? And here, the interesting situation is that you deform the theory with an operator with spins, right? And so the most familiar spinning operator is just a conserved current, like density operator, right? Let's say if you have let's say a free fermion, right, in 2+1D, let's say, right, and you deform it with this density operator, that's like the chemical potential, and then you get Fermi surface instead of Dirac point. That increases the number of degree freedoms. So yeah, maybe here something similar. And what's special here is the spinning operator used to deform your theory.
Okay, very interesting. I mean, if you have precise idea, don't hesitate to share them with me. I mean, we're puzzled there, but maybe there is something, yes, to if this occurs to. Yeah.
Yeah. Okay. Thanks.
Fredric, that was a great talk. I have quite a few questions, but maybe one question was about so this phenomena where the nu is direction dependent. What implication does that have for the correlation function? So if I just look at the correlation functions in real space, does that have some interesting form? And are there other models that are known which have this feature apart from? So are there other contexts where it arises?
Well, I think in for statistical physics, without I think it's very rare. I mean, I'm not aware. I think these anisotropy exponents different from one have been found for dynamical systems. So this is much more out of equilibrium physics. There, I think there are really many cases where it is known that we have such exponents. But for static problem, well, it means that the correlation function in one direction, if the two exponents are different, in one direction it will decay at a certain pace, and then if you go away from it, it will be slightly influenced, so there would be a crossover to the other exponent. I assume. So, but the correlation length, it's very different. I think it's clear, but it's very different from having just different correlation length in two directions. If you take the anisotropic Ising model, it will have the different correlation length, but the same exponent. Here, it's really the exponent, and this is something in the model we've looked at. Since this model breaks the symmetry, we assume that the principal axes somehow of these correlations are going to be X and Y. But this is not obvious. And from that point of view, Cardy's calculation is really remarkable, because his prediction is that the principal axis, he has a model that doesn't break the symmetry, and his prediction is that along the flow, the principal axis will actually rotate. So it's not an obvious property. So if you, I mean, why this is happening and how these directions are fixed.
And maybe one last little question. Just if you had to speculate to look for such phenomena in 3 dimension, what kind of models do you think would be the interesting places to start at?
In 3 dimension, whether there is such a possibility,
I guess first of all, is it even possible in 3 dimensions? And if it's possible,
this is what I was going to say. One would have to look. I mean, the basic idea that there will be some chirality, I think, should be present, but whether this operator is going to be relevant, I have no idea. I really don't know. I suppose this has not been really looked at because that came from experiments, all these questions from adsorbed layers in 2D. So I don't know what would be the equivalent system in 3D. But probably there are a number of things one could do. I think, in fact, Hughes and Fisher, their paper of 1984 discusses things in higher dimension and for different values of P. So, I mean, if you're really interested, maybe there are some answers to these questions about what happens in 3D in that paper, where you could look for something similar. But I'm not sure that something like the Chiral transition generalization in 3D non-conformal is predicted. I would have to read back this part.
Thank you.
Junchen?
Okay, so I'm very unfamiliar with this subject, but let me ask some naive questions. So this Lifshitz fixed point you are talking about, is it the same? I guess it's the two-dimensional version of the Euro Lifshitz fixed point in 2+1D. That in 2+1D it was the Lifshitz point described by z equal 2 and it's a Gaussian model. And this Lifshitz point, does it have any connection with it? Or I guess my real question is it dimensionally continuation connected to the 2+1 dimensional Lifshitz point? Or am I talking about?
I don't know. I mean, the thing is, you're asking me questions, the simple questions are the most difficult, as you know. So yeah. It's a I mean, what is clear, if there is such a point, it's just a multi-critical point between an ordered phase, a disordered phase, and a critical phase. And at that point, there is this is also a point where incommensurability sets in from the ordered phase.
That's very similar to the three.
I think it's the Lifshitz. I mean, the other contexts where I know Lifshitz points are really for this order-disorder transition when these are points where generally correlations become incommensurate but here it has a more precise meaning. So it's said to be a Lifshitz point, but it's yes, because it's a multi-critical, really a multi-critical point between three phases. I would have to think about it, or to look at the models you're talking about. So,
do we know the value of z here, or?
No, that's we don't. We know, it's if there is such a point on one side, when there is Pokrovsky-Talapov transition, there we know it is equal to. That's very clear, and but on the other side of the transition, this is precisely not known. We know at pots is equal 1, but then on the way and at the Lifshitz point, I don't think it is known. I don't believe it is known.
I see. All right, thank you very much.
Chen, I see your hand is raised, but probably it's still from previous question.
Yeah.
Okay. And yeah, if there is, well, let me ask you a question. So, can you play this game in other models, or POTS is somewhat special?
So I think this discussion applies to any commensurate incommensurate transition, and the incommensurate transition means that you have domain walls proliferating. They can be seen as fermions. So this discussion, this is why it is already ubiquitous, because it appears in 2D for adsorbed layers and in 1D. Then for this particular case, this is only true for period 3 and maybe period 4 phases. For the other phases, there is not even a continuous transition like POTS, and the transition has to be through a critical region. So it's really limited to this part. And for the Rydberg atoms, it's clear that also it's log 3 and 4. Now, if you're asking about simulations, that's something different. I mean, the CTMRG algorithm in 2D in classical system seems to be very powerful. It hasn't been studied or used very systematically, because in most cases we believe we already know what the physics is. But this is really a change of paradigm, and in many ways, the precision is much higher for such problems, at least, than Monte Carlo. That's very clear. But now in 3D, that would be very difficult. So in 3D, for instance, it has been, you can make 3D versions, but they are not at all precise at the moment. And presumably the bond dimensions you should keep would be enormous. So there is, I don't think we could play with this. At least at the moment, there is no real hope of doing anything better than either Monte Carlo or conformal bootstrap for the 3D-izing model, for instance. That's clearly not the case.
Okay. Well, thank you very much again for the nice talk.
Thanks to all of you for your attention so late in the day. I hope you get water again.
Well, hopefully tomorrow we will have water.
Okay.
Online.
I will be online tomorrow anyway. I will follow some.
Bye, Fredric. Thanks.
Thank you very much.
Bye-bye.
Okay, bye.
Thanks. Bye to everybody.
Stop share. Yes. I will leave.
Bye, Fredric.
Bye-bye. Thank you very much. Bye. Have some